All right, so we're going to fly through this. Basically, 1.3, we're talking about chemical and physical properties. So, a couple of points. Remember that basic definition of matter: mass takes up space. We know elements are the simplest pure substances. We know compounds can be broken down into elemental particles. And we know compositions are determined by the law of definite proportions. Now, don't let the law of definite proportions keep simple. So when we talk about the law of definite proportions, we're simply talking about that idea that it's always going to be the same ratio. Okay, so we're talking about a ratio of atoms. And in other words, water is always H2O. Nothing else is water, that type idea. Now, the other thing that I want to point out are all these diagrams down below. These are what you guys will be working with as particle diagrams. So you can see that I have atoms, and I know they're atoms because they're individual, okay, you can little round balls, okay. Now this is an element because it's the same thing, but it's a molecule because they're bonded obviously. Here you see a compound because I have multiple atoms, and here you can see a mixture. So you can see a variety of everything. So particle diagrams are going to be huge to your ability to recognize both what's going on in terms of identifying matter and in terms of what's going on when we start talking about the classification matter. Now, a couple of points real quick. Law of constant composition related to the law of definite proportions. So when we talk about constant composition, definite proportions, we're talking about something like H2O. We're talking about something like glucose, C6, H12, O6, etc. Law of conservation of mass, law of constant composition. Okay, in other words, the total mass at the end, constant composition. Oh, typo, guys, sorry. Okay, this is the law of conservation of mass. In other words, I cannot create or destroy mass. So the mass of a substance present at the end of a chemical process has to be the same as the mass of a substance present before the process took place. In other words, if I have hydrogen and oxygen and I form H2O, this is in essence what's behind the reason we balance. Okay, I know I have to have 2 here and 2 here, so I have now 2 times 2, I have 4 grams of hydrogen here, I have 32 grams of oxygen here. I have 2 times 18, so I have 36 grams of water here. Well, 4 plus 32 is 36, so mass is the same before and after. Okay, so here, pause the screencast, watch the States of Matter video below, and then answer this question in your notes. Okay, so the 2 things that you should have picked up on, okay, is you can see that there's disorder, okay. You can see that we have a lot of empty space. We know the particles have freedom of motion and they're far apart. We know that distinguishes a gas. With liquids, we see there's still disorder because they can still move over and around each other. And you saw that as you watched that solid melt. We went from a very structured substance to something that had less structure, had more movement, had more disorder, more chaos. And so you can literally see they moved over and around each other, but there was still no defined shape. Okay? So we see this, they still have free movement, but they're still very close together. And then here, when we get to a solid, we have fixed positions. So again, a couple of things, recognize. Ordered, we have fixed positions, packed together. Okay? If we look at, we have a liquid, we see disorder. We see the particles are free to move, but they are still close together. Okay? When we get to a gas, then we see its total disorder. Okay, notice the difference. There's empty space, we have complete freedom of motion, and the particles are far apart. So that gives us a distinct difference between the 2. A couple of things to recognize here is when we talk about cool or increased pressure, okay, notice that when we talk about something cool, we're literally looking at it in terms of energy. So what is happening to the energy as I go from a gas to a solid? And then what's happening to intermolecular forces? Break it down. Inter is between, molecular, we're talking the particles. So there is a trend happening with the intermolecular forces as I go from a gas to a solid. Okay, so if intermolecular forces are attractions, okay, between the components. Obviously, a solid is going to have the greatest amount of intermolecular forces. In other words, there's a lot of force being applied to hold the substance together. Whereas a gas, there's virtually no intermolecular forces because they are far apart and they have complete freedom of motion. So we know the intermolecular forces are literally increasing as we move from a gas to a liquid to a solid. Now, energy, well, energy, does it take more energy to be a solid or more energy to be a gas? Well, if we're talking about things, remember, this is where you have to go back and kind of remember a little bit from your freshman year. If I'm talking temperature and energy, energy, they're not the same thing, okay? When we talk temperature, we're talking kinetic energy, okay? A solid, a liquid, and a gas can have the exact same kinetic energy, meaning they have the exact same temperature, but they still have a different energy level. Because when we talk energy here in terms of our states of matter, we're talking about both potential and kinetic energy. So what we see is we see energy decreasing from left to right. In other words, a solid has less energy than a gas at the same temperature, okay? So, types of properties. We basically can deal with properties in terms of physical properties. We know we can observe this without changing the substance. Okay, boiling point, density, mass, volume, etc. Okay, in other words, I have a red rock. I can observe that redness without changing the identity of the substance. Okay, chemical properties can only be observed when the substance is changed. In other words, you don't know something's flammable till you see it burn. That idea. So that means changes. When we talk about a physical change, we don't change the composition. That's the kicker, guys, is you have to recognize that we do not change the composition of the substance. In other words, if I have H2O, let's get the pen here. If I have H2O, H2O is still H2O whether I see it as ice, okay, whether I have very structured ice, right? Okay, whether I see something very structured with ice and it's crystalline in nature, okay, versus when I see it in a glass. Okay, it's still H2O, whether it be a, okay, here, that's a terrible piece of ice. We'll just pretend. There's my piece of ice. Okay, so I have ice and I have a glass of water. The point being, I changed the state, I didn't change the composition. It's still H2O whether it's water or ice. Now, chemical changes. So chemical changes will always result in a new substance. Okay, if I take a piece of paper, I take my piece of paper and I burn it. So here's my little match. Here's my flame. I burn the paper. Okay, I end up with a pile of black ash. The paper was flexible. I could wad it up, straighten it up. It was kind of, it held its shape, it held its form. As soon as I burn it, I have this brittle black substance that falls apart easily. It can't be bent. It can't be reshaped. It's done. So that's a chemical change. I have something completely different that I didn't have before.